Again, chapter 4 is on heat and temperature. All right, so temperature is just a measure of how hot or cold an object is. So it's the level of energy of the molecules inside of the object. Okay, so something that is hotter, their molecules will move faster than something that is colder. All right, the colder the object, the slower the molecules move. Okay, and a thermometer is the device used to measure temperature or how hot or cold something is. So there's different types of thermometers. You have the alcohol-based thermometers. They use alcohol because it has a lower freezing point. One of the thermometers that are being phased out is the mercury-based thermometer. And that's because mercury is a known carcinogen, so it can cause cancer. So that's why the mercury-based ones are no longer being used. And then we have the laser thermometers that we've been seeing more lately. So they're touchless, which means they can just aim it at the object and be able to figure out the temperature for that object. So you've seen a lot of people have the handheld thermometers to measure people to see, if they have a fever from like COVID-19 or something like that. So there's different types of measuring devices for temperature. So it just depends on what your needs are. All right, so there are 3 scales of temperature. We have Celsius, Fahrenheit, and Kelvin. Now, the SI unit for temperature is actually Kelvin. Okay, it's not Celsius, it's not Fahrenheit, even though that's what we use here in America. All right, so the SI unit system, pretty much the entire international science community uses the SI unit scale except America. So we kind of have our own little thing going here. We usually, when we talk about the temperature on the news, they usually put it in either Fahrenheit or Celsius, but the SI unit temperature is actually Kelvin. All right, so here is just a comparison. So on the left, we have a comparison between Fahrenheit and Celsius. So here you'll see water boils at 212 Fahrenheit, 212 degrees Fahrenheit, and then water boils at 100 degrees Celsius. Water freezes at 32 degrees Fahrenheit and 0 degrees Celsius. So on the right, you have a temperature comparison between Celsius and Kelvin, which Kelvin, again, is the SI unit temperature for temperature. So here you have water boiling at 100 degrees Celsius, but it boils at 373 degrees Kelvin. Right, so for Celsius, water freezes at 0 degrees Celsius, but it freezes at 273 Kelvin. All right, so these are just comparisons between some of the major temperature scales. But again, Kelvin is the SI unit for temperature. Okay, so don't forget SI unit means the International System of Units. All right, these are the temperature conversion formulas. And I'm going to pause here for a couple minutes, maybe 2 to 3 minutes, so that you guys can make sure you have this on your formula sheet. So to convert from Celsius to Fahrenheit, all right, Fahrenheit is going to be equal to 9 divided by 5, multiplied times the degrees Celsius plus 32. All right, so, and make sure when you're doing these formulas that you're using order of operation. So if you remember PEMDAS or please excuse my dear Aunt Sally, so that's your parentheses, your exponent, your multiplication and division, and then you're adding and subtracting. Right, so anytime you're using these conversion formulas, make sure you're following the order of operation rules. All right, so Kelvin to Fahrenheit, that's where you have Fahrenheit is equal to 9 divided by 9 divided by 5, and then your degree temperature in Kelvin, minus 273 plus 32 degrees. From Fahrenheit to Celsius, you have Celsius being equal to 5 divided by 9 times your Fahrenheit minus 32 degrees, or 32, and that's in parentheses. So from Kelvin, Celsius to Kelvin, you add 273, and then from Kelvin to Celsius, you subtract 273. And then last but not least, from Fahrenheit to Kelvin, Kelvin is equal to 5 divided by 9 multiplied times Fahrenheit minus 32 plus 273. All right, so heat. Okay, so here we're going to learn the difference between temperature and heat because they are not the same thing. Okay, so heat is a measure of internal energy that has been absorbed or transferred from one body to another. So it's the transfer of energy from one system to another, or from the system to its surroundings, or from the surroundings to a system, right? So it's a transfer of energy. So your internal energy, that's the total kinetic and potential energy of the molecules of an object. Now, we talked about potential and kinetic energy in chapter 3, which was on energy. All right, so energy is the ability to do work. Your kinetic energy is the energy of motion. So that was the Ke equal to 1/2 mass time velocity squared. And then your potential energy, which is the symbol for potential energy, is Pe. So it's Pe is equal to mass times gravity times height. All right. So if you don't have those formulas on your cheat sheet, then you're a little bit behind. So make sure you go back to those. All right. So your formula sheet needs to be up to date every time we go over, a new chapter, because we're going to keep continuing to add more and more equations. All right, so your internal energy is what occurs inside of the system. All right, your external energy is what is occurring outside of the system. All right, so again, it's the total potential and kinetic energy. And the SI unit for both potential and kinetic energy is in joules. All right, so the unit of heat is the calorie, which is defined as the energy or heat needed to increase the temperature of 1 gram of water 1 degree Celsius. Now you'll also see heat in joules as well, and I believe I have a conversion on here later on in the slides that'll help you convert between calories and joules. Now, if you've ever heard someone say that they're trying to burn calories or calorie count their food or whatever so that they can get to a certain ideal weight or goal, the calorie is just the energy that they need in order to increase the temperature. When you increase the temperature, you melt away, your fat cells. Okay, so calories matter when it comes to diet and exercise. All right, so calorie is a measure of heat. All right. Heat, again, is the transfer of energy across the boundary of a system, resulting from a temperature difference between the system and its surroundings. All right, so as you can imagine, this light bulb on the right, the energy coming from inside the light bulb is warmer than the energy of the air surrounding the light bulb. Okay, so the light bulb is hotter than the air surrounding the light bulb. So that is a transfer of energy across the boundary of the light bulb into the air. Okay, so we use the symbol capital Q to denote the amount of energy transferred by the system. All right, so here we have Q is equal to MC delta T. Okay, so Q is the heat energy. M is the mass of the object or substance. C is the specific heat of the substance. And then delta T is your change in temperature. So this is your final temperature minus your initial temperature. So let me go and write this out for you guys on the whiteboard so you can see it. Let me see. So okay, we already went over temperature. Temperature is denoted by capital T. All right, and the SI unit for temperature is Kelvin, right? Not Celsius, not Fahrenheit, but Kelvin, capital K. All right, and heat, remember heat and temperature are different. All right, heat is denoted by capital Q, and the SI unit for heat is calories or joules, capital J. So this is calories. All right, and so the equation of heat is Q is equal to MC delta T, where Q is your heat energy, energy. Let me write that. That looks ugly. Energy. Okay, M is the mass. Delta T is the temperature difference. Temperature difference. And then your C is your specific heat. Specific heat. And that's usually a constant that depends on the material. So the specific heat of water is going to be different than the specific heat of air, which is going to be different than the specific heat of some sort of metal or any other material. So different materials have different specific heat constant. So this is a constant. Okay, so MC delta T is the same thing as saying mass times the specific heat times the change in temperature. So that's your final temperature minus your initial temperature. So TF minus TI. So delta T means change. Right? So Q is equal to MC delta T, where Q is heat energy, M is the mass, C is the specific heat constant depending on the material, and delta T is the change in temperature. So delta T is the same thing as the final temperature minus the initial temperature. So it's the temperature that you ended up at minus the temperature that you started at. All right. Okay, you also need to know the major phase changes. Okay, so melting is when you go from a solid to a liquid, similar to ice melting into liquid water. You have freezing, where you have the liquid turning into a solid. So an example of that would be liquid water freezing into solid ice. Evaporation is where you have the liquid that turns into a gas. So this is when you have like water that's boiling and you have the steam and the water vapor coming up from the boiling water, right? So that's going from a liquid phase to a gaseous phase. So be able to know these major phase changes and be able to give examples for each. Okay, next we're going to cover thermodynamics. Okay, thermodynamics is the study of heat. All right, we just discussed heat. That is the relationship of internal energy. All right, so thermodynamics is the study of heat and its relationship to mechanical energy. including the science of heat pumps, heat engines, and the transformation of energy in all its forms. So thermodynamics is pretty much a science of pretty much mechanical engineering. So any type of um, engine like that's in cars and trucks and 18 wheelers, your steam engines, anything like that that has a component of thermodynamics to it in order to, build those engineering systems. So heat pumps, refrigerators, um, washers and dryers, those applications all stem from thermodynamics. All right, so the laws of thermodynamics describe the relationships concerning what happens as energy is transformed to work, and the reverse, as serving as useful tools in meteorology, chemistry, and biology. So if you've already taken chemistry or biology, you already probably discussed thermodynamics. Right? You may not remember it, but you've already kind of covered these topics. All right, and entropy is a thermodynamic measure of disorder. So there's always some sort of chaos within a system. Okay, you're always going to have some sort of loss of heat or loss of energy. There is no perfect engine. Okay, so to measure that chaos or disorder, this is where entropy comes in. All right, so some of the end of class questions that you need to be able to answer for future reference.